All right, so consider a function. The output is going to be the output variable we'll call z, but really the key thing is the function has two input variables, x and y. So consider a function with two input variables and consider a specific point, a comma b. So, x is a, y is b. So then if f of a comma b is greater than or equal to f of x comma y for all x, y nearby ab, then f of a comma b is a local maximum or local maximum value, and f has a local maximum at a comma b. If you've got your inequality flipped, so if the z value at the point AB is less than or equal to the z value at points x comma y for all of these points x comma y nearby a comma b, or in a disk containing a comma b, then f of a comma b, so that actual z value, is called a local minimum or local minimum value, while we can also use the language f has a local minimum at a comma b. If that language of at is being used to try to talk about the input, whereas local minimum itself or local minimum value is to talk about the output, the z value. So look, a local maximum can also be called a relative maximum, and you can define similarly a relative minimum, right? Just like a relative maximum. And collectively, all the local maxima and minima, they're called the local extrema or the relative extrema. So informally, just like what we were doing earlier, in fact, I might still have it up here. Informally, just like here, local max is a peak and a local min is a valley. That same thing happens, right? For a function with two input variables. So there's something also yeah, let's see. Yep, local max is like a mountain peak and the local min is like a valley. So there is something analogous to an inflection point. So in Calc 1, we had this thing called an inflection point. There's a similar thing in Calc 3. Things are just a little messier here. So the point a comma b is a saddle point of the function f of x comma y. If there is a disk D containing the point a comma b, and then within there, you also have points x comma y where the z value is bigger at x comma y than it is at a comma b. But you also have points in the disk, points x comma y in the disk, where the z value is smaller than the z value at a comma b. So stated differently, a comma b happens to be a saddle point if the directional derivative at ab is positive for some direction u, and the directional derivative at a comma b is negative in another direction u, for a different u, right? So starting at a comma b, perhaps in a sense, some of the slopes are positive and some of the slopes are negative. So what does the saddle point look like? Typically, a hand-drawn picture looks like this. So there's this point A comma B that's kind of meant to be right here. This is meant to look like a horse's saddle. And so you see this kind of parabola-like look. It doesn't technically have to be a parabola, but it's got a kind of upward kind of look like this here, and then this downward look here, or maybe I've flipped my language here. But in some direction, if you just looked in slices one way, you'd think that the point you have is a local minimum, and if you looked at the slices the other way, you'd think you'd have a local maximum. This is hard to picture, I guess. And so, what about an actual thing that you know that could be used as the graph of the function? Well, it's really a Pringle, right? So if the Pringle, I mean, I guess three-dimensional objects have some thickness, but imagine that the Pringle was much thinner, like, infinitely thin. That would be the graph of a function. And then right there on the Pringle, right there, if you travel in some directions, you'd travel down, like so this way and that way. Whereas from this point, if you traveled in other directions, you'd go up. Right? The z coordinate would grow. So if a small drop of rain were to fall right on the saddle points, right there or right there, then the water drop might stay there for a moment, but shake the Pringle just a little bit, and water will slide down, or this way, right? In one of those two kind of directions, roughly speaking. If a small helium balloon were let go below the saddle point, so from here you got to go below, right? So from the Pringle on this top side instead, like see, you can kind of barely see the other side of the Pringle. So if I just try to, I can't do this any further, but I'm just trying to, go underneath here and then drop a helium balloon or let go of a helium balloon and have it lift up there. It might stay there for a moment, but if you shake the Pringle a little with that helium balloon stuck right at that saddle point, I'm trying to not this point, well, yeah, this point, but I'm trying to talk about this same location just directly under the potato chip, then shake the chip a little, and then that small helium balloon would slide up along here this way. Okay, so let's take a look at an example. The function f of x comma y equals y squared minus x squared happens to have a saddle point at the origin at 0, comma 0. Let's take a look at the contour map. Remember that the contour map is just a bunch of level sets, and so I have the computer drawing this for us. Okay, so right at the origin, there's apparently a saddle point. Notice that right at the origin, there's this kind of crossing of these two green lines. So this is the level set corresponding to output 0. And then if you, from here, travel, let's say, in the positive y direction, or the negative y direction for that matter, you're going to see the blue level set, that's the output 1 here. And then output 2, the red level set this way, right? So if you travel from, this is just the input space, right? But if you travel either this way or that way, starting from input 0, 0, the value of z is going to increase, right? From what, it's going to be 1 here, it'll be 2 there. Same deal, 1 here and 2 there. But if you start again at the origin and instead of traveling north or south, you travel east or west, take a look. You travel to the east, travel to the west, you end up hitting that level set in purple, which is the output -1. You keep going further and you hit the level set that's shown in black, and that is output -2, right? And if you're unconvinced, you can do things like, let's just throw in here. I hope you're convinced, but we could throw in a 0.5. Oh, this is also going to be in red. Well, that's unfortunate. But well, let me just turn it off for a second. I hope that seems to make sense, right? So there's the output is 0 over here. The output is 0.5. Then the output is 1. So using the contour map, this collection of level sets, I hope you're really seeing that saddle point, right? So at 0, 0, the z value is 0, and 0, 0 is on that green level set. From the point 0, 0, if you travel up or down, so you increase or decrease the y coordinate, the z value increases. However, if you start at 0, 0 and you travel either left or right, that is, you increase or decrease the x coordinate, the z value decreases. So up to there, we have an example. We have, I hope, somewhat convinced you that what we really have is a saddle point. Now, local mins, local maxes, and saddle points are all examples of critical points. So back in Calc 1 land, we'd think of like local mins, local maxes, and we'd probably consider those inflection points as critical points. Here, it's now these three kinds of things: local mins, local maxes, and saddle points. Those are the special points, which we'll call critical points. So we started with the Calc 1 stuff as a reminder. The reminder for these optimization problems from Calc 1 was, take derivative set equal to 0, find critical points, use second derivative to look at the concavity of the original, and then make some conclusions, check the boundary. All of these ideas are going to be helpful. So we, so far, have really just defined what local mins and maxes are and what saddle points are. And we've tried to just at least begin to describe what they look like. Now, what we need to do is talk about how do we find these things in Calc 3.